In this paper, we look into the problem of extrinsic calibration of event cameras mounted on an omnidirectional mobile platform. Our goal is to recover the relative rotation between the camera frame and the vehicle frame. We start by resolving the temporal offset TD between two heterogeneous sensors. Once the temporal offset is compensated, the extrinsic rotation can be worked out with an iterative closed-form solver that incrementally registers associated linear velocity estimates. Our contributions are as follows. Firstly, a rotation-free solution to the problem of spatio-temporal calibration for omnidirectional vehicle-mounted event cameras. Secondly, we build the solver on top of a canonical correlation analysis scheme. Finally, we proposed a speed-invariant image representation of event data. To hold the speed-invariant property while maintaining a good signal-to-noise ratio, we propose a novel representation by combining time surface and threshold ordinal surface by performing a logical AND operation on corresponding pixels of the two maps. First, let's assume that there is a 0.8-second temporal offset between the two velocities. The correlation between two velocities with a temporal offset is denoted by the correlation function r. When we apply an additional offset to one of the velocities, it affects the value of the correlation function. It is apparent that the correlation reaches its maximum when the temporal offset is 0. The correlation function r can be determined by the trace correlation. Using the covariance matrices obtained in the canonical correlation analysis process, the extrinsic rotation r can be determined through singular value decomposition of the product of the inverse of sigma VO, VE, and sigma VE, VO. We collect real data using an event camera mounted on a non-holonomic all-wheel steering mobile platform. By periodically adjusting the steering angle of all the wheels, we can obtain finger-shaped trajectories which are friendly to our calibration method. An example of 3 finger-shaped trajectory and the corresponding linear velocity information are shown here. As shown in Figure 1, we compared our method against various existing algorithms on real data. Based on the results, it is evident that our algorithm outperforms the others. In Table 2, we evaluate and compare the calibration results of using different image-like representations in our algorithm. The results indicate that the proposed representation method yields best performance. Finally, we hope this work can inspire new research in the topic of multi-sensor calibration that involves event-based cameras.